Just now I was doing the Wordle bot halfway. I got a functional agent, but it took so long for the agent to even do like one single guess. Okay, so just a recap of the Wordle bot. It's just taking the list of all possible words. Okay, then I get all the words. I have 12972 Wordle words. We have this function called guess word, which basically returns an array of 0, 1, or 2, signifying white means unmatched character and unmatched position. Yellow means the character is correct but the wrong position. Green means correct character and correct position. So this is the code that actually does the comparison. Okay, so the problem with the bot just now was that the code was a little too slow, because if we do this, this will take 5 n squared, where n is 5. So like it runs 25 times basically because of this double for loop here. Okay, so one thing that I did to change this function was to add in a memorize. Okay, what does memorize mean? Okay, so like memorize in dynamic programming is like to store a, something that has been previously calculated into an array. So I did some form of memorization here. Okay, so that I can omit like doing this 25 lines of calculation. Okay, so this is one thing. Okay, then in order to basically get the data back, so we actually store it in this guess word data dictionary. So the dictionary was initialized to be nothing. Okay, and then later on, after we do the memorization, okay, we actually will do this thing here. Basically, you if we undo this function here, we basically will look through all possible words. Okay, and then the first word and the second word. Okay, and put memorize equals to false, which means that we will actually calculate out this thing here. Okay, and then after that we will just put this thing in the entire super giant dictionary that has the two words concatenated as the key. Okay, so this basically makes the life easier, I guess, because later on, okay, so after that, after we get this whole thing, we will save this dictionary, and then if you want to, you can also like save this file, the pickle file, and then you can load it here. Okay, so then after that we also ran basically, okay, let me do another one, function to display game. Okay, so this is to display the game itself. Okay, it just takes in the list of guesses, list of outcomes. Okay, and basically does a display word. This is just actually a heat map. Okay, heat map is really great for this kind of tasks. Okay, after that we code the human game interface. Okay, so this was for humans to play. I guess we can try. So you can like key in your word, like maybe like arise. Oh, cloud. These are my two starting words, by the way. Yeah. Oh no! Wow, this word is difficult. Uh, oh no. the Okay. Let's just do any. Let's try. No, Go has a lot of things that is one. Oh, there's only one. Oh, that's amazingly little. How about wrong? Oh, nice. Okay, so uh, mm, wrong, going, wrong. I have no idea actually. I only know Tong, but yeah, I don't know any other words with Ong at the back. Okay, so let's say we don't know. So Muong. Okay, I definitely don't know this word. Okay, but anyway, the Wordle game that I created basically uses any word. Okay, I don't really want to limit the guess of the word to just the 2000s. Okay, because I really want this to basically uh, solve for any possible five-letter word in the dictionary. Okay, so this was a random agent. So the random agent, okay, you can see like let's say the target was apple. Okay, you just basically just guess the words randomly, and actually Wordle is not that difficult. See, it, even okay, so the random agent, there's a caveat. Okay, it doesn't just guess any word; it just guess all possible words that fulfill all the guesses possible. Okay, so if you just put in a starting word apple, I mean, if you want to key in another starting word, is fine. You can just let me know what you want. But this is apple. Okay, yeah. So if we key in a more obscure word like azure, wow. Okay, so yeah, this means Wordle isn't that hard actually. Yeah, you see, still can guess it pretty well, even with just a random agent. Let's try a harder word, I guess, rarer. Because like three R's, quite hard to hit, right? Yeah. Okay, so that's kind of spoiled the bots. You see, if you do a random agent with like this word here, if you are not efficient, it doesn't give you the word. Oh, sometimes it solves it. So the random agent is actually pretty competitive. If you evaluate the random agent over like 100 words, you can see that like on average requires 4.8 number of guesses. Okay, maybe what we can do now is rather than just returns number of guesses for the words, okay, we also return like soft within max guesses, whether the agent solve the puzzle. Okay, so this is a boolean, and then we return num guesses, which is the number of guesses for the word, which is an integer. Okay, so we have these two here. So we have num guesses, and we also return. Uh, so what we do here is we have another soft. Okay, actually we don't really need a variable called soft, but we can just return this. Or I could just do it here. And here if soft, okay, then we return soft here. So 5 comma true. So what we can do here is like this. Uh, okay, then we can then do like total guesses plus equals to num guesses. Okay, and then like total softs plus equals to soft. And we return two of them. Okay, so total average and okay, if soft, then we add this, and then we do this by divided by sort, by total softs. And softs divided by num words. So maybe we just put total words as 100. Softs divided by total words. Okay, let's try this. Very nice, and solves 92% of the time. Okay, so the random agent actually is not bad, right? You just do a random solve and like, and over here we limit our max guesses to 6. Okay, so if let's say so only when it's solved then we add up the total guesses. So on average, the random agent requires about 46. It solves pretty poorly though. Okay, sometimes it's good, sometimes it's bad. Okay, it's really random. Okay, as the name suggests. So the next agent that I was trying to do is this minimize worst outcome agent. So this basically means that, like, on average, let's say you can like guess a few words, and then you have a few states like this outer here, or this adore, like this kind of green 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 blank blank yellow yellow. So we try to bin them into all the possible states. Okay, and then we take the maximum of this. So this means that if you are very 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 unlucky, okay, this is the number of words that are left in your list. So we basically try to choose the guess, okay, that will minimize the number of words left. So let's try it out. Okay, so this is my agent. So let's say the word is like a zero. Let's try. Yeah, this actually takes quite a bit of time to run, so we have to wait a while. Okay, but it's actually because we have to look over this tool, which is like a huge list. Okay, so actually this agent is playing the Wordle game in hard mode. Okay, why is it hard mode? Because the words remaining is actually the number of words that are curated, that have already been like filtered out, that don't match the earlier hints. So this means that any words that are guessed after that will have to match with the hints above there. Okay, I mean it's hard mode because you can actually, if you let this word be the entire word list, you can actually probably get a better guess. Okay, because some words that are not possible might actually give a better outcome. So yeah, this is something that can be done. Okay, okay, but let's take a look at our agent here. So this was with Azure. Okay, so we need to wait a while for them to compute this double for loop, which can be very very tedious. Okay, so actually one way to uh like sort of cheat, okay, is, okay, not really cheat, but because we already know, like, for this agent, for the minimize worst outcome agent, what is the first guess. Okay, we can actually put it inside this we can actually put it inside this game. So if we change the game configuration here to have a first guess parameter, okay, so maybe I mean my favorite word is arise. Okay, but okay, so first guess will basically be the, because the agent, for all the agents we are going to code, it will be quite deterministic for what the first guess will be. Okay, the guess the agent will always make on the first move, if any. Okay, okay, we just put as none first. Okay, so this one will be a string. Okay, so over here, if num guesses equals to 0, okay, and first guess is not none, okay, else guess equals to first guess. So with this I can actually, like, hopefully shorten the time needed, okay, for this water bot, because I just make a first guess parameter here. Okay, let's just see ours. Okay, so the agent for this will always do Sarai as the first guess, so we can put that in. Let me just update this function here. Okay, so if let's say random agent, oh, hold on, what's this? Okay, it should be like this. If first guess is not none, else, yeah, like that. Mm, I guess we need to do like this. If num guesses is 0, if first guess is not none, okay, if there's a first guess, okay, then we will do this. Yeah, I guess we have to do like a more roundabout like that because we need to cater for this case here where it's a first guess, and also if it's not the first guess, then we do this. Guess word, guess, comma, target word. Oh, okay, I get it. Okay, because if num guesses is 0, if first guess is not none, this should be if first guess is none. Actually, we can compare. Oh yeah, I did wrong logic. If num guess is 0 and first guess is none. Okay, this means that if 0 and this happens, if not, okay, I think I know what's the issue. My logic is wrong. Okay, this is a simple if else logic. Okay, yeah. What I wanted to do is really this. So only in this condition, okay, then we make guess is first guess. If not, we do that. Okay, so this should work now. And then if we want like first guess to be something, we can put like first guess is arise. Okay, so yeah, so like that we will see that the first guess is now arise like this. So I guess if you put the right first guess, you might be able to like score better. Let's just try. Okay, so if we do evaluate agent, okay, and then maybe we just put like first guess. Here first guess equals to first. Okay, because this will help reduce the state space a lot. So like maybe first guess we put as arise, my favorite word. Let's see how well. Oh, you see 94% of the time. Oh, you see we're just changing the first guess. It solves so much. Okay, I mean if you try a very crappy guess like fuzzy, yeah, you expect it to solve lesser times, I believe. Yeah, so on average it's not. So we try Sarai, that there's now the like it's like arise like that. Actually it's not that great, right? It doesn't solve as much as, I mean we could do like an average of this, but well, I'm pretty pleased to see this. This is my favorite starting word for Wordle. In fact, I always use arise as the starting word. Well, it looks like it does pretty well, even just for a random agent like that. Okay, so for the more advanced agents like this, okay, this is minimize uh words remaining. So if we want it to be like not hard mode, we can put this to be all the words. Okay, but let us just see. Okay, because it takes quite long to run this. Let's just make first guess equals to Sarai. Okay, because we already know that it will. Oh, you see, it's now pretty fast. Okay, because after we eliminate the starting words is actually much faster. So maybe we can try Apple now. Okay, how about let's see, what else should we try? Pedal. Oh, okay, that was fast. Okay, so maybe um something harder, fuzzy. Oh, not too bad. No, it's really not too bad. Okay, so we can also run this evaluate agent thing. Okay, so maybe actually what I should do is I should just print this here. Okay, so yeah, then I don't need to. No, actually, I shouldn't. Yeah, maybe I shouldn't. Keep it separate. Yeah, I'll just copy and paste this whole thing here. So let's make sure the random agent is still working. Okay, so we try this here. So this one will be the agent will be the minimize worst outcome agent. Okay, it's actually a function. I mean, I could make it a class as well, but I think this is fine. So this one will be minimize worst outcome agent. Oh, wait a minute. My first guess is wrong. It shouldn't be arise. It should be Sarai. Okay, but let's see how well arise works. Okay, so meanwhile, oh, 100% of the time. Not bad. Okay, this is only 100. Okay, because like due to the uh, time constraints, I mean, I didn't run over all possible words, but it looks like it's not too bad. I mean, we can try running over 1,000 words. Okay, see, it's taking a while. So I will run this offline and then like put it in my blog, like how it works. But I think this minimize worst outcome agent should be quite good. Okay, because the Absurdo uses this technique. Okay, to counter you. Okay, it basically chooses a word, right, whereby you will have a lot of words remaining. Okay, so this actually is a direct counter to the Absurdo strategy. I think this will perform quite well for Absurdo actually. Yeah. So this should be the direct counter to Absurdo, and I think this is not too bad. Okay, I mean this basically just assumes that the adversary is out to make you guess wrongly, to make you get the worst possible guess. Okay, but it may not be true, of course. Okay, so actually having this like first guess thing has helped us to solve quite a lot of the like optimize quite a bit, because if we keep having the first guess constant, we save a lot of evaluation, especially the first one. Though actually this works on hard mode, and actually I think it works pretty well. So the next thing I'm gonna try to do is I'm gonna try the three blue one brown approach. Okay. Okay, I mean it's not really his approach actually. It's actually information theory, right? I mean, if people who have watched information theory, is basically the it's just using this equation to tell you like how much randomness there is. Like this one, this is the equation. H equals to negative sum I pi log 2 pi. So the information theory approach is like this. Entropy, or basically the amount of information. Okay. Oh no, that's it didn't solve for some of the time. See, 99.4% of the time. Some of it didn't solve, but it's pretty good. I think those that didn't solve are the less common words. Yeah, but I guess this is like hard mode, right? So if you let it not do hard mode, it will probably solve it all the time. Okay, so anyway, for entropy, it is see the equation again, minus pi log 2 pi. Okay, minus summation over all I. Okay, pi log 2 pi. I wonder if can do latex over here. Yeah, latex in markdown. Can I do it? To write inline latex, do a dollar sign. Oh, okay. I can do latex. Negative sum I, pi times log 2 pi. Yeah, that's essentially what we are trying to do. Okay, so essentially the agent will be very similar to this. We can just copy and paste this thing here. Okay, and maybe we just call this the entropy agent. This agent minimize the entropy that could occur after a gas. Okay, so basically this makes the probability distribution of gases much uh, more uniform. Okay, so I mean, it theoretically helps to counter. I mean, it is very similar to this approach where you minimize the maximum number of popular words that could remain actually. Yeah, so this is very similar to this entropy. Okay, because like if we make the probability distribution more uniform, I mean, I look at, if we take a look at probability distribution and like if we make it more uniform, okay, like instead of making it like this, okay, we make it more flat. Essentially, you are making the top part, the one with the highest amount here, we are making it lower as well. So it could be similar, I mean, to the to this approach here, but it allows for like certain picks. So like let's say if like we have a very bad probability, but that I mean we have something that is like very high here, okay, but I mean it may be very low chance of occurring, then it won't factor very high in this entropy here, okay, because you need to factor two factors, log 2 pi and this pi. So basically before that, let me just try to code out this entropy. So let's say if I have a probability distribution, let's say 0 0.2, 0 0.2, 0 0.3, 0.5. Okay, then maybe let's do a function for entropy. So define get entropy. Okay, so this basically given a probability distribution returns its entropy. Okay, or the information content. I mean, it depends on how you view it. So what we do is we have this probability distribution. Okay, but we may not uh, it may not be a probability distribution. Maybe we just call it frequencies. Given a list of frequencies. Okay, because the frequencies are just outcome, and then from there we need to calculate probabilities. Okay, equals to mp dot array frequency divided by, okay, sum frequency. Okay, so this will give us the probability distribution. Okay, but we of course need to have like certain stuff like epsilon. Okay, so later on we can add this epsilon inside this, because like if log 2 0, what is log 2 0? Okay, so 0 log 0 is 0. I mean, in cloud challenge, okay, so actually we may not need the epsilon after all. So we can just do, okay, for prop in probability history, okay, so we can get the sum, be like entropy is 0, okay, entropy, okay, so we need to get the prop, okay, times log 2. I think there's an mp dot log 2, right? Yeah, I think I think there is. So numpy dot log 2. Actually, we can do log also. I mean, no difference, right? I mean, it's just a scaling. If you do log or log 2, your entropy will still be similar. So numpy dot log 2 prop. Actually here we do minus, okay, because this is a minus sign. Okay, if prop, okay, so we don't add in the zero because zero log zero is supposed to be zero, defined by Claude Shannon. Okay, so we have a probability distribution and then we get the entropy of this. Okay, so this is about 1.48. So it's more or less shown that this if we have a distribution that's more or less uniform, we should get the lowest possible entropy. Let's say we have 222. Okay, but if I get something like 522, oh, something's wrong here. So I'm supposed to get a lower probability if everything is uniform like that, as compared to like not uniform. So there's something wrong here. So let's print out this probability. So this one will be like 0.5 log 0.5, this 0. Oh, okay, so essentially this is actually lower, okay, because there's one less term, like one outcome is totally gone. Okay, so if we make this like 0, yeah, I'm not sure whether I did it correctly, but if let's say we have a list of probabilities and then um, some of them are 0 already because of like there's no chance of it happening, it should give me like 2. Okay, but if let's say I have like 100 over here, yeah, because the probability of this happening is very high. Okay, but after this happens, like I wouldn't really want to get a bin with 100, right? I would want to get as even as possible, right? So maybe I should maximize my entropy rather than minimize it. So this one means I'm very like certain that this is correct, which is not ideal. We want to like ideally, okay, so we should try to maximize the entropy, because if we maximize the entropy, we get a distribution like this, which is all very even, and the distribution is flatter as compared to if we have like 100 like that. Yeah, so actually this is correct. This is correct. We are supposed to maximize the entropy, and then this would happen. Okay, so and then this will give us okay, by maximizing the entropy, we get a flatter probability distribution over all possible guess outcomes. Flatter probability distribution, okay, it could mean that uh, means lower chance of getting an extremely high number of words remaining. Okay, I mean in the 3 Blue 1 Bell video, he also used something like information bits. Okay, but I think that's not necessary. Okay, basically we just want to make the probability distribution flatter. Okay, we can just treat information theory as making the probability distribution flatter. Okay, and because of that, we minimize the chance of having an extremely high number of words remaining. Okay, so I think this is the function. I think I coded it correctly. So instead of doing, okay, the max guess, okay, so the best max guess here will be 0 now. Okay, and then now if best guess greater, then this one will be entropy, get entropy. Okay, so I don't want to print the probability distribution anymore. uh, yeah, this looks pretty good. I think I got the right formula. Okay, so this is the entropy agent. Let's try to do a simple game, like maybe fuzzy as the word. So this will be entropy agent. First guess is none. We want to see what the entropy agent gives us as the first guess. So let's take a look what the entropy agent gives us. Okay, so like triple one clown, he got something like crane. That was with incorrect thing. I think his latest word is something like, I can't remember the word, slate. Uh, Not important to me. I mean, I will just stick to arise, which is my favorite guess. So this entropy agent, let's see whether or not. Okay, this is played under hard mode, by the way, because we still give it only the words remaining here. If we give it the entire dictionary to guess, okay, perhaps you'll be able to find guesses that actually minimize the space of possibilities, and that could be better actually. Okay, but for now, we just assume that we like to play hard mode, and these are the words remaining that we can use to guess. Okay, which means we only can guess words that match whatever we have before. I mean, I could also maybe that's why the minimized worst outcome agent couldn't get all of it like that. Maybe it solves 99.5. Maybe we have to make it not play in hard mode. Then it might solve 100% of the time. Okay, but let us see what the entropy agent gives us as our starting word. Okay, I'm quite curious to see what is the starting word that they will give us for this. Okay, so it's sure taking a long time because I guess this entropy distribution I need to do like I need to divide by the total number here and then like do this. I guess if I do like uh, the probability distribution, I just plus an epsilon term. Maybe I don't have to do this, and then we could just sum the whole thing up. That might be faster. Test. Oh, this is actually quite similar to what he got. Test. Okay, so first guess will be test. Okay, seems like test is a pretty good word. Okay, so let's try something like a zero. Okay, belly. Not bad. Not bad. This hard mode, by the way. So wiser, something like that. Okay, riser. Oh, what happened? Oh, there's no riser in the. In oh no. Okay, so if we do hard mode guessing, turns out that uh, we may not be able to get everything. Okay, let's just try entire word. Least index out of range. Why? Oh, it should be words. Oh, you mean there's no such word as rises in the dictionary? Let's try belly again. Belly is not a word. Cannot be. I must have done something wrongly here. Okay, I guess I'll try going back to what's remaining because using the entire list was pretty okay. So I think that's fine. Bells. Okay, so there are cases if you go by hard mode, it doesn't solve at all. Okay, I'm just curious if I were to, because over here, um, while guess not equals to target word. Okay, so actually I can incorporate my non hard mode agent here. Okay, because like you see cases like this, I think it's really quite tough for the AI to guess because like if you only have one letter left like this, you confirm cannot make it in six tries. Okay, so I don't think it's possible for hard mode to solve all the time in six tries. Okay, especially if you land cases like this where there's multiple starting letters. So maybe what we need to do is we need to do it for all possible words instead of just words remaining. Okay, and then here will just be words. Here, actually, we can just do this for word in words, and we can just change this later. I don't get the issue here. So there's a key error welts. Okay, it means that the target word is yeah. I just want to see what caused the key error. So this is what they test. So okay, it's like printing all possible pairs of guesses. It is like a super brute force approach. I hope I don't break the. Yeah, I'm just curious why it did not work out. So let's see. So I wonder if the just using a deep Q network can solve this problem already. Because it does seem like it's a discrete case of 12,900 over possibilities. DQN might be able to solve it with enough training episodes, I guess. Okay, I think I shouldn't print all of the words. It's stop. Oh no, I think I think it might have crashed. Let's try to stop this. Yeah, so somehow like if we go to welts, it didn't really work out. They have a key error. Okay, I need to debug it because I'm not sure why is there a key error because you're supposed to take both words, the word itself as well as the target word, unless there's something wrong with the target word here that causes this agent to fail. Okay, so looks like test is the starting word that is most chosen. Okay, which is quite good I think, like because you see you have S and T ARE. I mean, if you talk about like RSTLNE, you have RSTE. So you have like a lot of it, very common letters, and I quite agree that this is like this potentially a very good word to use. It's just that I prefer a word with more vowels. Yeah, and yeah. S, S and T and R, all are great letters to use. Okay, so now what I really need to do is to get the kernel to stop running so that I can. Okay, so I made a mistake. I should have printed out because there's so many things to print out here. Like double loop, right? Let's see whether I can interrupt this. Yeah, I think it has run amok. Oh, yeah, my kernel can't be stopped. I guess we'll just wait a while for it to be interrupted because I did start the interrupting process. Yeah, this print function actually takes up a lot of bandwidth, so maybe we should just cut it out. Yeah. Hello, Element. Yeah, no, I just wanted to try coding out what I like saw on like videos, and yeah, eventually, actually, I hope to do something that will require zero like human intervention. So it will be great if the computer can figure out like some form of information theory based approach. Well, actually, I'm also thinking whether or not like we can do it without information theory because the probabilities. Yeah, three blue, one brown. Yeah, I watched his video. So yeah, now I'm doing his like similar approach. Yeah, but I think maybe if we do like minimize variance, that might work also. Because like the earlier agent I did, I just basically uh make sure that the worst case outcome is as low as possible. So this is my minimize worst outcome agent. Okay, so this is the direct counter to Absurdo. I mean, we play Absurdo before they do this technique. Okay, whereby they try to make the outcome of the guess, okay, leave you as many remaining words as possible. So this I would say is the like minimax agent to Absurdo. Okay, by making sure that the words remaining is as low as possible for the worst possible outcome. Yeah. So yeah, but this one, I mean, all of the agents are actually done like with the hard mode setting for Wordle, so you can only guess from the words that fit all the previous clues. Okay, but this, I think there's going to be some words that you can't solve. Okay, because like if the words happen to have the first few starting, like you have four correct words and the last four correct letters and the last letter cannot be found, sometimes the last letter has more than six possibilities. So in cases like this, I think the hard mode will confirm fail. I mean, that is if you do like greedily. Okay, but I guess if you could do like multi-step look ahead to realize that you will reach that state, then you might be able to avoid it, avoid getting four greens. Yeah, yeah, but yeah, those I think you can use reinforcement learning to solve it. Okay, right now I just hope that my kernel can be stopped. Okay. Oh no, oh no, it's not stopping. It's not stopping. I don't really want to reconnect. It took very long to get my because I actually did some form of caching in the guess word function. It's like telling you what the guess would be. Yeah, because if I were to do this function out directly, it would take like O n squared time, which is like 25 times to do per word. Yeah, so I actually stored in a massive lookup table. Okay, okay. I guess we have to force terminate this and then like potentially like reload this again. Oh no. Restart kernel. I mean, I hate to do it, but looks like we have to restart. I just wonder how long it will take to load the data. Restart kernel. Yeah, so it turns out that for even for the entropy agent, you are still not able to, if you limit the words to just the hard mode words. Okay, if you just use a single greedy look ahead to just choose the next word that maximizes the entropy, okay, you may still not be able to guess it within 6 tries. Okay, so I guess if you really want a very competent agent, okay, you probably need to take into account more than one step. Okay, maybe 2 or 3 steps. Okay, but the compute is quite immense. Luckily for this game, the state space goes down quite fast. Okay, I'll need to restart my kernel. Yeah, so yeah, we'll get back to this later. Okay, I think what I'll do is I will like force restart this. So meanwhile, let me just how should I do this? I Sorry, which outcome function are you talking about? Yeah, no, I would like to show you this. Okay, but the problem is now it's stuck running this cell. Okay, I need to find a way to stop this. I think what I'll do is maybe I will just run another program. Hold on. Yeah, just give me a while. Let me go and on another. Let me run it in another desktop. Okay, so the 92. I mean, I have some cloud GPUs. Okay, I'll just run it on another one. Okay, all right. So let me just run this here. Can you see this? Yeah, I hope you can see this. Okay, so I basically ran it on another on on another server. Okay, so this was the server that like died. So I run it here. I hope it will be okay. Okay, so it looks like this can work. Let me just off this. Okay, it's like it's like lagging. That one was lagging. Okay, so we have this. I will need to redo my Wordle bot again. Okay, but instead of doing the whole memorization again, thankfully I have this guessword data which I saved earlier. I can just do this pickle.load. Oh, I need to import pickle. Okay, uh, so yeah, while waiting for this, let's see. Okay, so just now my function crashed, so I'm not going to do the same thing again. I'm going, because I printed out all the words, I'm going to remove the printing. Okay, then I think I will possibly just do in words remaining. Yeah, I mean, I'll just keep it to be like hard mode and then let the let, let the game decide like whether or not you win or not. Okay, so we are going to load this pickle. Okay, this might take a while to load. Okay, because the file is 4.2 GB. Okay, let me tell you how many lookup table entries are there. Okay, it's 12,900 times 12,900. Okay, which goes up to a grand total of, I don't know. I mean, if you do 12972, So these are the total is 168,272,168,272,784. So these are the total number of entries in that lookup table. So we're gonna import. Oh, okay, it's not done. Okay, I thought it was done. Yeah. So this will take a while, but it will be like 5 to 10 minutes. That's why I was quite reluctant to change the kernel. Okay, but just now due to a mishandling of the printing function, the whole thing destroyed. Okay, so I mean, since I'm waiting, let me just go through like what was done. So this basically just uses the SNS heat map, okay, to print out the board state, okay, the guesses as well as the outcomes. Outcomes are like the color of this. Okay, so there's 0, 1, 2, 3. 0 is gray, 1 yellow, 2 green, and 3 white. Okay, then this is the game interface for playing with like yourself. Okay, for the board, this is the game interface. Okay, so the guess word over here, uh, the pickle file is 4.2 GB. Yeah. Oh, has it loaded? No, not yet. Yeah, so this will take like 5 to 10 minutes to load. Okay, and after it's loaded, okay, we will have the entire guess word data here, which helps a lot. Okay, it helps a lot because if you need to do this function all the time, right? Yes, I know. Yeah, but the problem with this is that the memory requirement for this lookup table is quite huge. Okay, I mean, I know if you were to limit the number of words for Wordle to the 2000 possible end goals, like, there's only 2000 words in the curated list, right? That can be answers, 2000 over words. If you limit it there, then I don't think you need this. Then your lookup table will be more manageable. Like, it's 2000 times 2000. But my lookup table is huge. It's huge. Oh, how do I do that? I mean, this is what I did for the pickle. I already did like protocol is highest protocol. Mm, yeah, I guess I could do that. Yeah, I could do that. Instead of using a dictionary, I could just use an array. Yeah, I could use an array and then I can omit the keys for the dictionary. You're right. You're right. Yeah, I think that's possible. I can try to do that offline. Yeah, because now I'm just hoping that. Oh, it loaded. It loaded. Everyone, it loaded. Oh, thank goodness. Yeah. Yeah, thanks for the suggestion, Element. I agree with you totally. I think I can do without the dictionary. Okay, because the key for the dictionary is the two guesses. The guess and the target word combined together is a 10-letter key. If I omit that, because I already know all the words, right? I can actually like reverse engineer the key itself. Yeah, I can actually do with less data. Yeah, that's one thing that could be done. Okay, so now we have the guessword data. So let's see like guessword data like welts. Do I have a word called welts? I'm just curious. Welts, melts. Okay, good. So we have the guessword loaded. Okay, let's do the function to display the game. Okay, then we just anyhow do a sample game. Okay, okay, okay. I just want to like lose the game here. Okay, so this is a sample game that can be done. Random board. Okay, let's try. Okay, so we make sure that it can work. Okay, very good. Okay, and then like we try this. Okay, I took away the print. Yes, I took away the print. Okay, okay, so let's stop this. Okay, we try for 100 because it will be faster. Then we do the entropy agent now. Take away the print function. Yes, this is the offending one. Offending print function. Okay, so it's, oh, now it's also 100% of the time because first 100 words. 3.62 guesses. Okay, so you see, Wells is one of the failure cases. Wales, how about Wales? Okay, so if we don't let it go to all the possible words, then there might be a chance of failure. So now we let it look through all the possible words as the guesses. Yeah, it always fails here. Not sure why this happens. I mean, if let's say I do like abyss, yes, yes, yeah. So the key error is like word plus target word, right? So somehow like the guess itself is not reflected. Let's try something. I mean, we just make sure that it looks like it only happens when there's like one word remaining. Like from the petre there, actually it can solve already. Okay, because there's only two words remaining. Okay, maybe I can print out here. Okay, if length words remaining smaller than 10, print word. Okay, now I don't make the same mistake as just now. I only print if the guess is less than 10. Okay, somehow printing this. Oh, yeah. Okay, the game function is like this. The game function is here. So it takes in an agent, okay, the guess and the max guesses, and then basically what it does is that while the guess now is target, not let's say it's target words, okay, we will pass this to the agent, okay, and then based on this guess here, we then do the outcome here. Then over here, I guess one of my new words could be a void word. Yeah, because if the guess is like a void guess, I'm not too sure because this didn't like fail for the others. Maybe what I can do is I can print out words remaining. Yeah, I I mean if we just look at this, you can see that the keyword is alerts, which means that the either the word or the target word is not there. Mm, okay, let me try this again. Let me try this again. See, it's all here. All of the alert is there. unless there's no more words left. Like unless my guess is I know. It could be that there's no words left, then my best word is nil. Okay, because if I put my best word here as alert here, I think you're right. Because sometimes the entropy can be zero, right? If you are yes, you are right. Yes, yes. So this was the issue. Thank you, element. Yeah, you are absolutely correct. Yeah, so we should set our entropy to be negative so that this, or we can set this to be greater equal to. Yeah. Eh? Oh, okay. There's an issue here. So after it, okay. Let me just print out max gas here. Let's print out best max gas. Okay, I just want to see. Okay, we probably need to remove away the, yeah. So the last part is wrong. Okay, so it's nothing. It's something to do with our words that we have. Okay, because if we put this as words remaining, this is there's no problem here. It's only when it's words then there's problem. See, zero. There's one possible word remaining. Okay, let's try that again. So it means that when there's only one possible word remaining, we should just guess that one word, right? Because like for word in words, okay, I guess cigar is the highest entropy once there's only one word left. But we shouldn't do that. Like see, zero. Cigar is zero. And I guess if we guess alerts, this would hit all the clues. I guess the entropy is zero. Okay, so very simple. You can just do this. If words remaining, like that. Yeah. Yeah, okay, done. So basically, I I think what we can do is we can just basically set this to just, because there's something wrong with the entropy when there's only one word remaining. So if there's only one word remaining, this probably distribution. Maybe you can just investigate over here. If there's only one word remaining, okay, what will be my entropy for this? Okay, what will be the entropy? Yeah, it will be always zero for any word. Okay, so that's why like it will just pick cigar or something. Yeah, so if there's only one word left, okay, we don't need to gain any form of entropy anymore. Like we don't need to gain any information anymore. We can just output this. Yeah. So I guess if it's greater or equal, right? Yeah, if it was just the words remaining, it will be fine, okay, because the only word remaining will be alerts. Okay, but because we want to increase our guess outcome, okay, we will guess with all possible words. Okay, same thing for this. Let us do the same thing. So for word in words, okay, and then here we will do word equals to word, and then this will be word, let's try this. So this is no longer hard mode. This is basically easy mode. Yeah, because I just want it to be able to solve. Wait, what happened? Oh, it's taking a while to load this, is it? Oh no. Okay, I lost connection to the server. Wait, let me just try. Yeah, but it looks like it manages to solve the word. Oh no. Yeah, I guess I'll have to stream this another time when my server is up again. Yeah. Yeah, somehow, yeah, this is the problem with like remote GPUs, I guess. Yeah. But it looks like the entropy agent does perform better most of the time. Okay, it does look like it's performing better. And yeah, I think I'll run both the minimize worst outcome and the entropy agent across all possible n words. Okay, and I also let it guess in easy mode, so we can let it guess across all words. This will require more time. Okay, but I hope I can continue. Okay, I just reconnected. Can I recontinue from here? I'm not sure actually. I mean, I just reconnected, but I'm not sure whether they will let me just continue from here. Reload. Yeah. Okay. So I think I'll just end here. All right, and then basically we just see based on some experiments that I'll do which one is better. Okay, then I will try to do some agent that like maybe minimizes the mean. Okay, or actually mean is not a good way because yeah, I'll try to do the file compress as well. Yeah, mean is not a good way because all based on regardless of the guess outcomes, the mean will always be the same, right? Because uh, the mean is just the total number of guesses across each outcome divided by the number of outcomes, which means that the mean will always be the same regardless of what outcome we have. Okay, so maybe I can try something like variance. So instead of doing information theory approach, we can try to just minimize the variance. The minimizing variance has worked quite well for like some deep learning papers. So maybe a variance might be a good enough measure. We don't have to do probabilities like information theory. That could be something that we can try to explore. And yeah, so as you can see, the site has some issues. And yeah, we'll continue this another time. Okay, yep. Thanks for watching. Yep. See you, Element. Yeah. Bye bye.